Hello, how are you doing? This is Mike here, and in this video we're going to talk about an important topic of how to convert or express ordinary functions parametrically. So how to convert a function of x to a relation between two parameters. So how do we go from a function of x to a set of parameters? And this is actually a lot easier than it sounds. So there's just it's a very simple process, and it's nothing that's too extensive. So all you have to do is just was what I do. Let x equal to t. I let x equal to t. And again, remember, t is any independent variable that you want. But I usually choose t because that's consistent with my calculator. So that's why I let x equal to t. So if x is equal to t, this will yield the relationship of x equaling to t and y being a function of t. So y equaling to f of t. So now in this circumstance, we can write an equation or a curve into a parametric curve. So let's go ahead and try an example. Let's go ahead here and try an example. So let's say that we have, let's say we just have a nice trig function. We'll use cosine of x, and we'll have this restricted between negative 2 pi and 2 pi. So for us, this guy will start up here. He'll dip down, come back up, and this is from negative pi to 0, and then we're going to go from 0 until 2 pi. So this is our t equals 2. Oops, oh, sorry, I haven't done that yet. So now we want to convert this. So I graphed it. Let's go ahead and convert this to a parametric equation. So parametric equation. So I'm just going to let x equal to t. Therefore, everywhere I see an x, I plug in a t. So then y equals to cosine of t. Y equals to cosine of t. And we know this same relationship existed for x. Remember, this was a relation of the domain. This was a relationship of the domain. So therefore, since x equals to t, then this is defined. This is only defined for when t exists at negative 2 pi to positive 2 pi. So this would be t equals to negative 2 pi. This is negative 2 pi. This would be t equals to negative pi. This will be our t equals to 0 up here on top. So it'll be t equals to 0. This will be t equals to positive pi. And this will be t equals to positive 2 pi. So that's a very interesting or easy way for us to convert from a regular curve to a parametric to two parametric curves. So to two parametric equations, and drawing a regular curve to a parametric curve, which is two parametric equations. So let's go ahead and just talk about our relationship of functions being one-to-one. So remember, if a function is one-to-one, so I will let you go back and review your college algebra, and I do have a YouTube video on one-to-one functions on my YouTube site. So if you want to look that up, you're more than welcome to. But if a function is one-to-one, then we know that its inverse function is also a function. So then we can express its inverse as f to the negative 1. We'll just write f to the negative 1. We won't say x at this point. We'll just say f to the negative 1. There we go. It's horrible handwriting today. I'm so sorry. So, and this is its, not with an apostrophe. Express its inverse as f to the negative 1. So in this case, y equals to f to the negative 1 of x. And that's equivalent to x equals to f of y. So therefore, you can express the graph of f inverse in parametric form by introducing the parameter. So you can do the exact same thing. So you can express express the graph of F inverse in parametric form by introducing the parameter y equals to t. So before we let x equals to t, and now we're going to let y equals to t, and this will yield this relationship. So x is now a function of t, and we know y equals to t. So, so this is actually a really interesting way. And actually, I find this substantially easier in converting between a function and its inverse back and forth. And you guys will love this. So let's go ahead and just look at an example here. Let's look at an example. And let's say we have f of x equals to, I don't know, x to the fifth plus x plus 1. So we can rewrite this parametrically as letting x equals to t, and therefore y is equal to t to the fifth plus t plus 1. So this is the parametric form. This is parametric. Oops, I'm sorry, of f of x. This is the parametric form of f of x. However, imagine if I asked you in algebra, in college algebra, to go back and say, now, everywhere you see a y, replace it with x. Everywhere you see with x, replace with y. Then go ahead and solve for y. That would be horrendous. So how would we write the parametric form of f inverse? And you guys are going to love this. So the parametric form of f inverse of x is just this. So now we're going to let y equal to t, and then x will be equal to t to the fifth plus t plus 1. So that is how we'd write the equation of f inverse of x. So I'm just as a simple example. Remember, if in college algebra, if we said let f of x equals to, I don't know, 2x plus 3. If we wanted to find the inverse, you would replace f of x with y. Then everywhere you see an x, replace it with a y. Everywhere you see a y, replace it with an x. Then we'd have to solve here by subtracting 3 on both sides. And then we'd have to divide by 2. And we know that f inverse of x would be equal to x minus 3 over 2. That's how we would determine the relationship between f of x and f inverse of x. And we do see that these are inverse one-to-one functions. But this would be very, very tough for us to solve in terms of y, almost impossible by hand. But now using parameters, we can do this relatively fast. So if we wanted to on our calculator, so where's my calculator? Looking at my calculator here, let's go ahead and look at this guy. Oops, turn him on. So let's look at this guy here. So in terms of the function, I would have t, and then I would have t to the fifth power, t to the fifth power plus t plus 1. And when I hit graph here, we're going to have this graph. So now let's graph its inverse. So our inverse we'll do in the second curve. So here I'm going to do t to the fifth, t raised to the fifth, plus t plus 1. And then I'm going to go down here and just put in my t, and I'm going to graph these at the same time. And notice, if I were to graph the line y equals to x, these two would be symmetric about the line y equals to x, and therefore I would conclude safely that these are in fact the inverse function. So clearly I find it much easier to write inverse functions in terms of a parametric relationship than I would ever want to do using our same functional curve as we did back in algebra.